Let's get it started. Hope everybody are doing fine this morning or maybe this afternoon. There are some folks attending the course from other part of the world, and I'm so excited to have another course with Whitson. So to be honest with you, this is the first time this course is being offered. And now when I started to collecting some material, thought maybe only 2 hours could be enough to cover the contents. But at the end of the day, I ended up trimming some contents so to fit in not only 2 hours but 3 hours. And there are a lot of material going to be presented today with the intent of getting you guys have your hands on some exercises to be familiar with the functionality of numerical model in Whitson Plus, and try to cover almost 70% of the content, and the rest of 30% are going to be a quick overview how you can access and what circumstances you may need them. So I'm happy to have another opportunity to get connected to you folks. There are some familiar faces, some familiar names, and we'll be happy to start the course. So two of my colleagues, Felix and Daniel, will be helping me today. If you have any question, please make sure to send them in the chat. If you can cover in the chat, definitely these folks will help me to address those. If not, we have some break time, so I try to stay in the break during the break as well. So we can address those questions like directly. Hopefully you can see my face and you can hear me, more importantly. And I would appreciate to keep some housekeeping for the meetings, keep your camera and your audio muted during the session, so we can have a very smooth meeting. So to start with, some meeting logistics. So over 100 people registered for course. So far 60 plus people has showed up. Hopefully we can see more people attending. The course is intended for 3 hours. Going to be break it with two break as well. With a question, and we try to address them as much as possible in the chat. Otherwise, during the break time or after the meeting, I would be happy to have an individual session with you folks to address your questions. So to start with, I want to make sure that everybody has access to the software so we can do the exercises together. So what I want you to please open your browser and goes to courses.whitson.com. This is courses.whitson.com. And by the way, the course is recorded, so if you think you're going to miss any step you want, because the recording will be available after that. So if you go to the course.whitson.com, you should be able to see this numerical modeling in Whitson 2025. If you click on that, you should be able to put in these credentials. So this is the email that you register with. It's not your company email, it's the email that you register for this event. And for the password, it should be Whitson. Yeah, it should be Whitson. I put it wrong here, sorry. Whitson Numerical Model 2025. So make sure, yeah, this is correct actually, sorry. It's Whitson Numerical Model 2025. So if you have any issue with logging in, please let us know in the chat so we can address that before proceeding to the course. Hopefully everybody can log into the courses at Whitson. So let's proceed. So a little bit of introduction about Whitson Plus. Today we're going to cover Whitson Plus, which combines many different modules. Some of these modules are intended for unconventional reservoir, primarily multi-frac horizontal well, but there are a lot of modules that is in regard of the well geometry or the permeability of the reservoir. So like DCA and TIFL are applicable to any type of the reservoir. PVT and phase behavior. We have one section in PVT in Whitson Plus, which deal with initialization of PVT. We're going to use it for pretty much any analysis and any type of calculation, including bottom hole pressure calculation. So bottom hole pressure calculation, we need it for any numerical modeling, including production data analysis. So that's also integrated part of our workflow today. Flow balance. With the flow material balance, it's also applied to any type of reservoir. It's not limited to unconventional reservoir. For the focus of today, it's going to be mainly on numerical modeling and also numerical RTA. So we have two sections in the production data analysis, rate transit analysis. One of them dealing with the data analytically, the other one is dealing with the data numerically. The precursor for full physics reservoir simulation model is this numerical RTA, and I'm going to show you what are the best practices to integrate these two pieces together. It's always recommended as a starting point to start with a numerical RTA and then see the numerical model with the result from numerical RTA. Nodal analysis also just integrating reservoir and the wellbore. So it's also integrate part of our workflow. We don't cover that today, but I'm going to show you how we can use the result from numerical simulation to see our nodal analysis on the IPR type here. And there are some well tests. The well test analysis, we're also developing some new tools that would be able to do analysis on the routine build up data that we may have in the conventional, unconventional wells as well. The other piece of software that we have is the Whitson PVT, which fundamentally focus on the PVT studies. So we're going to skip this very quickly. And as some of you may know, next week we are holding an event. It's an annual event, VidCon 2025, is being held in Houston in person. Some of you have already registered, I know that. And for those of you that you didn't get a chance to register, there might be some room still available. Get connected with Jessica, and she will be able to help you for more information. And highly recommend this is a technical event where people utilize Whitson software on day-to-day application to come up to how they solve their challenges, everyday challenges. So you may know that some of you may attended these courses in the past. These are list of courses, and it's also growing. We also have another courses lining up for the rest of the year. These are so far courses that we have covered. If you are interested in any of these courses, the recording should be available as well as the slides. So this is today we are covering numerical modeling, but the results of numerical modeling is somehow integrated with the rest of the modules, so it's not standing by itself. Also, it is also recommended to get a certification, not for the sake of holding a certification, but mainly all the new features that we are including in the Whitson. You may not be aware of that. These are great starting point for refreshing, also for the refreshing, like what you learned in the past. So what's the new feature has included, we try to keep them as update, pretty much daily updating these certificates. So if there's a new feature being added, we're going to include it into this certificate. So it's all the thing is visual, so they are supported by a lot of GIFs, so you guys can take a look at that and quickly get an idea if you are interested in some new feature, how you may incorporate it in your analysis. We have a lot of support, so you may have experience that we try to get back to you as soon as possible. For everything, we treat every ticket as important as possible. And anytime you get connected to us for any feedback or any you saw any inconsistently in the result, we will be happy to get back to you. So don't hesitate to reach out to our support team. And okay, so this is as I said, mainly focused on the unconventional reservoir. By unconventional, I mean multi-frac horizontal well. This is typical workflow that we started. Also for today's analysis, some of the actual production data, we start with the PVT and fluid analysis, and we do the calculation of bottom hole pressure. These are the main ingredients that feed the rest of the analysis. So we teach the PVT and bottom hole pressure, then we're gonna do some analysis, production data analysis. Multi-phase FMB is giving us an estimate of how far we have contacted the reservoir fluid in situ, and we're gonna take PVT information as well as bottom hole pressure information. And then we do production data analysis. These production data analysis can be done analytically and also numerically. We're going to have one slide dedicated what are the difference between analytical and numerical, and in what circumstances we are recommended to use full physics numerical simulation. And once we do the numerical simulation, so we're going to focus on this part of the step 5 of the workflow, which is simulation. And once we get a qualified history match results, I'm going to talk about what is defined as a good history match, what criteria we need to meet on the good history match, and then we're going to use that history match to forecast. So as a reservoir engineer or as a petroleum engineer, there are two main goals that we need to honor. First of all, how much fluid do we have in place, and the second goal is to forecast it. So these two we're gonna cover in this workflow. So let's start with the numerical model, and there's basically three components to the numerical model: simulation and forecasting. So in the first place, I'm going to highlight the importance of analytical and numerical simulation. With the analytical solution, as you may know, it's the exact answer to an approximate solution. So we're going to make a lot of assumption here. The fluid has constant PVT, constant viscosity, constant compressibility, flowing at a constant rate, and pretty much 99% of the cases, all of these assumptions are violated. But once we made those approximation, we're going to have an exact solution for those approximate problem. What's the strength of these analytical solution? It gives us a lot of very quick idea about the well performance comparison. A lot of you guys are using the analytical solution to come up with a square root of time plot, and based on the slope of the plot, you're going to have a quick comparison of the well performance. So that's how we do a very quick comparison between the well performance in the same pad in the same area. On the other side, we also have numerical solution. This numerical solution or approximate answer, because we basically discretize our reservoir simulation into a smaller grid block and try to solve mass equations, conservation of mass equations on those grid blocks and solve the equation all together at the same time. What the strengths of these methods is that they consider all the physics, changes of the PVT, multi-phase flow, relative permeability, and also changing operating condition. So if we be able to do handle the complexities as well as heterogeneity, which is most of the case, 99% of the case, these are the real world conditions that we are dealing with. So in comparison, analytical are simplified setting, numerical are real, dealing with the real complexity, but with the advent of very robust numerical simulation, you can still, with the speed of analytical solution, you can run those numerical simulations well. So to just summarize it, analytical solution, exact answer for simplified problem, numerical solution or approximate answer to exact problem. So these are the fundamental difference between the two. Each of them has their own strength. So the reason why I provided this to highlight their strengths. So we're going to work on through their strengths rather than weaknesses and complement, and they are complementary to each other. So this is what I decided to put in. Once you can drive a Porsche, which is numerical simulation, why settle for Camry? Despite the fact I receive a lot of comments on this, I would rather run a Camry because it's much more stable than a Porsche. But we're going to offer this solution to drive a Porsche and see how the ride would be different. So this is the intent of these. You may have in your career be dealing with a lot of numerical engines, so these are listed some of them. But in Whitson, what we use is the OPM flow, which is an open source, but we customize it to our favor. There's no interface to open or OPM, as far as I understand. But in Whitson, we working through that interface to basically tweak the parameters and get the result out of that. All of these in numerical simulation are black hole numerical simulation. By black hole, I don't indicate the phase. It's basically it's the numerical simulation black hole versus composition. The compositional modeling, we trace each of the component by itself. In the black hole, we only have two components, which is oil and gas. Basically, water is also flowing, so three components. So let's get into the well model fundamentals. There are different type of well available in Whitson. The first one is multi-frac horizontal well, which is basically the focus of these talk today. And the second one, we also accommodate the vertical for radial well. It's a vertical well in the center of radial model, and it's mostly designed for the conventional type reservoir. And the third one is a vertical wall, but there are a stack of multi-fractures, a stack of fractures completed in different layers. It's good for vertical wells, which is still stimulated through hydraulic fracturing. So you can define different layers, as many as you wish, and see those layers, different properties, porosity, permeability, and this is kind of towards the vertical wall completion as a matter of fact. So, the representative well model that we have here is a multi-frac horizontal well, but this is kind of a pre-built model. So when you open the interface, you come up with some pre-populated fields that define the properties of the matrix and fractures. And it is a typical multi-fracture horizontal well in the tight reservoir. The dimensions are user-defined, but you can change them according to your need. And at the end of the day, what we simulate is only a quarter of fracture. And this quarter of fracture is highlighted here. This is the element of symmetry. And you can imagine at the end of the day, we're only using a quarter of fracture to represent the entire maybe 4-mile lateral length of the wellbore. That we believe there are a lot of heterogeneity along the lateral length of the well, but still, in most of the cases, we are expecting a very good history match results. So we need to take that into our consideration when there's a mismatch between our data and our model. What can be the source cause of that? The primary part of that will be the heterogeneity along the lateral. So, and on the production scaling, we simply multiply by 4, which basically this is the element of symmetry. Multiplied by 4 is one hydraulic fracture, and multiplied by number of NF, which represent all the production from the well. Same in Whitson, same in any other numerical numerical models that accommodate this element of the symmetry. This is the way that they do it. So let's move on and talk about the 3 elements of the talk today, which is history matching and sensitivity analysis and probabilistic. History matching by itself, this is the interface that you're going to see. So it's highlighted on the top. History matching, sensitivity, and probabilistic. So we're going to talk about all of these fields and what information goes into all of these fields, and also highlight if you change some of these parameters, how would it impact the history match? So we're going to have some field case examples as well as some synthetic example. And let's start about some of these. So what does history match mean? As the name implies, we're going to change the parameter to simulate the result that is aligned with the actual production data. And the sensitivity, so once we are done with the history matching, we can also forecast that model. And the sensitivity analysis is basically what if scenario. I put 100 natural fractures, 100 hydraulic fractures into the well. What if I reduce the fractures by 80%, by 20%? So 80 fractures, how much cumulative would it get me in 3 years period? So we're going to do a lot of sensitivity analysis on pretty much all the parameters that we adjusted into history match step to see what would be those impact. Including, we can do a lot of well spacing optimization, drawdown strategies. These are some of the day-to-day questions that we are asked on how we can run this sensitivity in our wells. So I'm going to show you some of those examples as well. And finally, probabilistic in the world of reservoir engineering, dealing with the subsurface. Nothing is unique. We're going to deal with a lot of non-uniqueness, and how to address them is the world of probabilistic. So for the range of permeability that we are dealing with between this amount and range of all other parameters that goes into the history match, what are the 100 realization that we can get from the history matching practice? So probabilistic is the ultimate answer to any numerical model. is very critical in the sense that it's communicating risk and uncertainty to the forecast section. So some of these modules are going to deep dive into them, but some of them, because for the probabilistic, at least we need to run 300 cases to come up with a reliable answer, so we can do the forecast based upon those range of uncertainty. But because of the time and also because of the resources that we need to allocate at the same time, I'm going to introduce it, and I want you to pursue for your own models. So let's start with the history matching. So this is in the history matching, there are different sections. I'm going to introduce them to you, and I'm going to walk you through what we're going to see once we open any of these cards. So in the well and reservoir data, when you click on this edit button, you're going to see this interface, and this interface, there are a lot of information regarding the matrix as well as fracture properties. I'm going to show you that. You will see they are color-coded by black and blue. So black numbers, in Whitson, when you open any of these modules, there are some default information pre-populated. And once you started to adjust some of these parameters, they turn from blue to black. So it's a very nice way of distinguish what parameter you have changed and what parameter are defaulted from the software. So it gives you more basically awareness on what parameter you have already changed. And so this is the basically I want to walk you through all of these fields one by one and let you know what does these means. So lateral length of the well is clear from this plot. It's basically how the estimated volume, like it's from top perforation to the bottom perforation, from top to heel. Number of fractures as how many fractures we have completed in the estimated installation, and it could be depending on the way of completing the wellbore. It could be pinpoint completion, plug and perf completion. We have some uncertainty in the number of fractures, so you guys may have better idea talking to like the surveillance, the monitoring technology that you have deployed. How many of these fractures basically are active fractures or producing fractures out of the number of fractures per clusters times the number of stages, which is the total number of fractures. Maybe 70% of them are effective, maybe less, maybe more. Fracture conductivity is simply we don't deal with seeding the permeability of the fracture. Instead, we work with the FCD, which is dimensionless fracture conductivity. A rule of thumb is 100. So below 100, the threshold is 100. Below 100, it is defined as a finite conductivity, which gives you an extra pressure drop from tip to the horizontal wall location. That's extra delta P is the finite conductivity fracture. And this is the way it is defined. It is the conductivity of the fracture divided by XF times permeability of the matrix. Fracture height is the propped open fracture. So your reservoir thickness may be higher than this one, but we have a lot of uncertainty in the fracture height as well. XF is something that we can do have good idea from production data analysis, but it is the extent of the fracture itself. And reservoir half length is basically your well spacing from one well to another well is XF. Reservoir half length. Reservoir height is most of the cases these two are said to be equal, but it's also the geologist should give us some idea about what's the effective reservoir height is. Matrix permeability, this is another parameter that we are looking after. Can we have some idea about the matrix permeability once we do production data analysis, and matrix porosity, and also rock compressibility. Rock compressibility, there's very limited data from the lab on measurement of rock compressibility, so we are using a correlation, Hall correlation. Usually for the high pressure reservoir is underestimated. So it's definitely need to multiply this by 2 or 3 for high pressure reservoir. Fracture gamma and matrix gamma are the two parameters that we do in our modeling that the define pressure dependent permeability. So most of the cases, specifically in the very high pressure reservoir like Hinesville, as the pressure deplete, the net stress, net stress on the reservoir, on the pore space increases, and that cause reduction of the pore throat, which is directly correlatable to the permeability of the formation. Therefore, the permeability drop and these two features basically accommodate the productivity loss due to permeability reduction once the pressure is depleting. So these are some of the advanced features. Put it in the appendices. If we got some chance, I'm going to demonstrate the use of all of these features, depending on how much time we get at the end of the meeting. On the fluid initialization, this is how we initialize the fluid into the matrix. So this is the interface when you open the interface. This is what you're going to deal with, but essentially this is very similar to the PVT section. So we have this fluid initialization as an alternative way of adjusting the PVT. So it's a very quick way of adjusting some of the parameters, but it's very similar to taking the step to the PVT section and adjust those parameters. So they are kind of linked. So if once you change some of the parameters here, they're going to show themselves in the other module as well. And finally, the relative permeability. This is also in the realm of numerical simulation. Definitely, we cannot avoid relative permeability, even though we are running some cases of 100% saturation. Like if you want to model an aquifer, you still need to provide this information, relative permeability. Therefore, it is really important to have a very good understanding of what are each of these parameters means, right? And what's the best recommendations and best practices to come up with a representative relative permeability data set for your modeling practices. So there are two sections in the matrix and fracture, as you can see here. And because we have two medium that are somehow interconnected, which is matrix and hydraulic fractures, so therefore we define two sets of relative permeability. There are a lot of options in saving these sets of relative permeability if you're going to apply it to the same well, which is highly recommended if you're dealing with the simulations of multiple in the same path or multiple in the same area. You intuitively expect to apply same sets of relative permeability pretty much to all of your wells, or if you want to tweak them, you're going to tweak them very lightly. So that's the functionality of saving these sets of relative permeability. And I'm going to walk you through each of these fields and let you know what does those parameters means. So let's start with the relative permeability. So we have two medium, therefore we provide matrix and fracture. For fracture, it's much easier than the matrix itself because fracture is like open conduit. It's very similar to the pipe. So the relationship between the saturation and relative permeability is much easier to explain in the fracture than in the matrix. Pretty much all the fractures, we can apply the same sets of relative permeability, which is a cross-shape, X-shape, because fracture are open media, but for the matrix, we're going to be totally different story here. So let's investigate these relative permeability parameters. So on the oil and water relative permeability, these are some of the parameters that you need to input. First one is the matrix critical water saturation. You see it represent critical water saturation. And on the curve, it is basically this point on the x-axis where relative permeability is still 0. So this is the threshold that below that value, the relative permeability is 0. Above that, there are some values. So these are, despite the fact that they are sitting on the x-axis, but these are non-zero. So essentially, if your permeability is, if your water saturation is close to 20%, I would say, still effective relative permeability is very close to 0. But this is basically set the bar for 0 and non-zero value. The other one is matrix K relative to water at residual water saturation. I'm going to talk about residual water saturation, but this is basically endpoint relative permeability. You can imagine that so this value is changing between 0 and 1. And so all of these parameters, except the exponent, I'm going to talk about that, can change between 0 and 1. And so I set it to 70. This is basically in the 70 on the y-axis. And the third one is the matrix exponent for water. So this can be changed anywhere between 1 and above 1, basically. So, but the typical number for these, it can vary anywhere between 1.5 and 4. I'm going to show you how to adjust. So you can see this curve is, there are 3 parameters that govern this curve. So we're going to see how changing each of these parameters will impact the ratio, water-ore ratio in this case, because we are dealing with the oil and water relative permeability. On the oil side, also, we are talking about residual water, saturation oil at the residual water. So this point here is set to be 10. This is basically from 100. If you move to the left 10%, this is residual oil saturation and residual water. The other parameter is endpoint relative permeability to water, to oil, which is this way, it is set to 0.9, and similar to the exponent for water, it is exponent to the oil as well. Similarly, for the oil and gas, we have similar parameters. So this is residual gas, S of O at residual gas saturation. This is matrix relative permeability to oil at critical water saturation, and this is also exponent of the oil. Critical gas saturation, it is similar to critical water saturation. So below that, relative permeability to gas is 0. Above that, there are some value associated with that. And this is endpoint relative permeability to gas at residual oil saturation and O of gas. So I'm going to show you some of how adjusting some of these parameters will impact the gas oil ratio as well. So this is a cheat sheet. The cheat sheet highlights which parameter to change along the production life of the well. So if you're interested to see some bump into the producing GOR, you will rather change the critical gas saturation. So if you increase the critical gas saturation from 0 to 20, what you're dictating is that from 0 to 20, if gas evolve out of the solution and break out of the solution, until its saturation reached to 20%, it wouldn't move. So you are basically surpassing gas production and keeping that into the reservoir. And if you're you're trying to match the GOR production in the middle life of the wellbore, you would rather change the exponents. And finally, throughout the life of the end of the production life, you would rather adjust the endpoint relative permeability. So this is provided here. So take your time. We can also generate some synthetic cases to showcase so how adjusting some of these parameters can impact the GOR profile. So the only way that we can learn them is to create some synthetic cases and adjust this parameter accordingly to see the GOR profile. And similarly, for the what impact the water-ore ratio, or similarly water cut, is again early time it will be critical water saturation, late time it will be endpoint relative permeability, and in middle production life would be basically exponents of the phases. Okay, so in the history matching, there's also one field associated with the time stepping. What's the use of that? Time stepping, this is a description from the manual. Whatever I'm presenting to you, all of them in much more detail is also included in the manual. So there is 3 different options that we can select in the time stepping. The first one is all, when the numerical simulation basically taking all the data points to predict the rest of the phases. So if you are assigning bottom hole pressure to be your boundary condition and selecting all of the data point to be the case, therefore it's simulated all the uploaded time steps without skipping any point. Smart is in the first 100 data point is working as all, so it's taking all the data point, and after 100 data points, it's basically work through each hence time step afterward. And custom, it is you that decide how quickly you want to skip between the data point. For instance, number 7, if you select number 7, each 7th number, multiples of the 7s, will be selected as a history matching data point for predicting the rest of the parameters. So the recommendation here is always have a smart if you want to have a very quick answer, or maybe custom if you want to quickly, if you have 100 days of 1,000 days of production, I would rather go with a custom with a 10th data point to have an idea about the range of my parameters that can confidently history match the data. And once I am close to my final solution, I would rather have one run with all the time steps, despite the fact that it's taking much more time to run the simulation, but it's giving me some confidence that I'm honoring all the time steps. So as a first example that I included in the for this course is the practice of relative permeability, and we're going to work through one example to see how adjusting some of those parameters can impact the profile from water ore ratio and gas ore ratio. And specifically, this example is tailored for critical water saturation. So it would be a good starting point to also get familiar with the software. So hopefully, most of you guys were able to sign into the courses. And if not, if you have some problem, please let us know so we can help you with getting there. So once you're into this interface, you please go ahead on the top right of the site, website, and there's a Add Project button here. And click on Add Project. And once you click on the Add Project, you need to provide a project name. So to be able to work through this example independently and not to step on each other's shoes, I would recommend to create a project and name the project whatever you wish, so it's be unique to you, so you know what project you're working on. In this case, I'm gonna name my project my initial and my full last name, and click on Save. And once I click on Save, this project is created under my name. So if you can go ahead and please add project and set the name so it is unique to you, could be any name. And so we're gonna work through examples in our own dedicated project. If you do so, I'm expecting to some project are showing up here. Perfect. So for 31, so I urge everyone to please create those projects. We're going to work on this project. So once those projects are created, if you have hard time, you can easily search them. So it is my project. I can search my name and click on my project. Now, any well that we're going to create in this domain is going to be stay in this domain. So in this case, we can have wells with the same name, and we're going to work through those wells, but there's no interference between my well with the same name as your well. So here in this interface, all the way to the right of that, there's a mass upload button. If you click on the mass upload, then this interface will pop up. And to the right of this interface, there's an example. On the examples, click on the example, and on the bottom, there is a RTA certificate. So we're going to use these wells that we have in the RTA certificate for the numerical simulation as well, and click on upload. So if you click on upload, it takes a few seconds to upload 3 wells. And once you do that, you can close this window and 3 wells should show up. So these 3 wells, we're going to work for with one of these wells, and this name Kite, the first well in the list. Click on that one, and this is what we're going to get. For those of you that's the first time working with Whitson, I'm going to quickly walk you through some of the basically detail that you can better use this interface to your favor according to the size of the monitor. So you can always click on Control and middle button on your mouse, adjust the zoom to which is basically best fit your monitor size. So this is good enough for me. And so as you see in the first page, it's called scenario page. We provide a lot of information on the reservoir properties as well as well information and completion metrics. So some of these properties, if you change, edit some of these, you're going to be dynamically changing throughout all the modules that we have. And so let's see, the porosity is defaulted here. Rock compressibility is used through the correlation, Hall correlation. And so with the completion metrics, if you provide some of this information are not necessary, but if you provide it, it definitely would be helpful when it comes to the comparison plot. So if you have thousands of the balls and you're going to group them, you're going to bin them, you're going to see the performance of them, you're going to see how much, if the GOR profiles for some of those wells are drastically different from other wells, what would be the source cause of that? Are they bonded wells or are they like open wells, so standalone wells? So despite the fact that this information are not necessary, but it is recommended to fill this information as much as possible because it will be really helpful once it comes to comparing and contrasting well performance using these completion metrics. On the production metadata, this is all the information here are grayed out because they are all calculated based on the production data that we have. So this is much of information, as much as information that we may need to proceed with the workflow. So on the workflow, we're going to start with the PVT, take a look at production data, and go to the bottom hole pressure, because these are the two most important ingredients for doing an analysis. And we're going to go to a numerical RTA and numerical model, because this is numerical RTA, this is production data analysis, but using a numerical technique. So it very well fit into this course. So let's start with the PVT. And with the PVT, we have one full dedicated course for PVT. But the easiest way to initialize the PVT is to click on the edit reservoir fluid composition. And what it shows here is the GOR of the well. So in this case, this is an oil reservoir. And you can see by default, only 100 first days of production are presented. So you can see there are a stabilization level. There's some area of the cleaning out. So you may argue which is the representative GOR profile of the well. I would argue that this is the stabilization level. So when everything clean out, so I can safely represent this GOR to be my GOR of the well. And the reservoir pressure is all of these information are from SPE repository. So we didn't decide if the reservoir pressure is how much. This is coming from SPE. So we believe these are the good number to start with, but we are always want to also double check. Is it a fair number to set in for the initial reservoir pressure and reservoir temperature? So for instance, some of the things that you can do, you can take a look at the TVD of the completion and come up with the pressure gradient and also temperature gradient to see if those numbers are making sense or not. So if you click on save, you can create your PVT phase envelope. This is at the same time, you can also view the composition of the representative fluid based on that GOR. So if you take this composition and put it in any PVT simulator, the initial GOR should be very close to what we set 750 to be the GOR of this producing well. On the PVT table, there's all of this information are sorted out in the PVT section. So you can export them to any third-party software, and you can take a look at them. You can, if you're going to do any further calculation, you can export Excel. And I'm going to give you a tip here. Once you open up in Excel, and it will, there are some tabs that are hidden. So they are purposely hidden. So only main information are provided here, but you're welcome to take a look at them. You can unclick on these, and let me edit this one and unclick, click on this and make them unhide. So there are a ton of information, extra information here. If you want to take a deep dive into the PVT, these are basically, or they are all available to you. So let's proceed. And the second part is to go to the bottom hole pressure. Hopefully everybody follow. Otherwise, let us know. On the bottom hole pressure. So this is the bottom hole pressure. So for this well, there are one set of the data that's is provided as a gauge information. I can clearly see this is not a gauge because of all the spikes and valleys that we can see. We are expecting the gauge pressure to be much more smoother than this, but we're going to accept, and this is the gauge pressure. So we can also calculate the bottom hole pressure because all the wellbore configuration also are provided here. And this is the range of a spread of bottom hole pressure calculation through different correlations. Beggs-Breel, Hagedorn and Brown, Waldesmeyer and Gahar and Gray. And you can see for this spread, like in the mid production, Waldesmeyer and Gahar are predicting 571, and the gauge is 1700. So there's 1,000 psi pressure difference between these correlations. So which one is the correct one? So Whitson did a very comprehensive study of bottom hole pressure. I would be happy to share that paper with you that compare the results of these bottom hole pressure correlation against the gauge pressure, where the gauge pressure were available for different fields. And this gives us some good idea about in the range of GOR, producing GOR, which one is more trustworthy. I just wanted to highlight this, that we're going to use this, we're going to select one of these bottom hole pressure, and or we can customize one ourselves, and therefore we should be aware of which one we are selecting. So once that we are working through the bottom hole pressure, so there's also other plots, accompanying plot that are created. One of them is the liquid loading. So this was apparently is on the gas lift. So there are some gas lift being gas injected into the wellbore, and the more important plot is this critical rate, which is expected. This is the critical rate that we need to have to lift all the liquid out of the wellbore. So I'm gonna get back to this later as well. For now, I'm gonna use the measured PWF gauge to be the representative bottom hole pressure for the rest of the analysis. So once we calculate our bottom hole pressure, then we can move on to the either numerical RTA or numerical model. I would rather start with a numerical RTA because you also get to know this interface and how to correlate the result from this one to the numerical model. So let's start here and click on run. So these are some of the time stepping. They say that it's defaulted to be a smart, which is also my choice. So I always start with a smart to get an idea of the directionality of the solution space that I'm dealing with. So if I click on run, this is the four interface that basically 6 of them we are getting here. And more importantly, the intent of this exercise is to get an idea what adjustment do we need to provide to the relative permeability parameters, get a good history match on the water-ore ratio. So as you can see, specifically with the multi-frac version, so well, we got a lot of questions that do we need to honor the water production data or not? And the answer is depending on what's the source of water production. If the water is coming from the reservoir, therefore it's the volumetric that you are withdrawing through the reservoir, therefore you have to honor that. If the water is coming from the aquifer underneath the reservoir and you frack into those aquifer, you need to model the aquifer, but you cannot model the aquifer very effectively. Therefore, you may safely argue that the water, well, because there are a couple of issues with the water, first of all. First of all, it's not being reported properly. But if you believe it is being reported properly, as there's no allocation issue, etc., then we need to honor that. So in this case, I can clearly see the model is under-predicting the production data. So there's 2 ways that I can accommodate adjustment to the model to predict better production rate. One of them is simply talk to the geologists, invite them over coffee and ask them, please, can we have instead of 32, 54 or something elevated? And in this case, they say no, so we're going to stick with that. Then we're going to see what other tool we have in our toolkits. So one we have is to edit relative permeability. So here in the numerical model is edit relative permeability. Relative permeability is here is a little bit different than the numerical model. So if you click on that one, you see this interface. So in this interface, you already know all the parameters that goes into that. And I'm going to quickly simply adjust this matrix critical water saturation. Now it's set to 20. What it's dictated is up until 20% water saturation in porous space, it is immobile. So what if I reduce it instead of 20? First of all, it's changed from blue to black, indicating that the user has adjusted that. So if I reduce this one from 20 to 10 and click on save, this exclamation mark indicates something has changed in the reservoir model. Therefore, click on run to get the most updated parameters into the model. And I'm gonna scroll down and see, for instance, this model predict the water-ore ratio or water cut doesn't make a difference between the water-ore ratio. In this case, is maybe it's better to take a look at the water cut. Or okay, that's fine. So we can see how adjustments of relative permeability will impact the model prediction of water cut or water-ore ratio. The early time, yes, I believe that I put the valve for the simulation process. So a lot of these water is coming from the flowback, the supercharge, etc. But later throughout the production life of the well, I believe that it's rule of thumb after 6 months in some reservoirs and some basins and some of them, depending on how much water you may have, the load recovery 50% of load recovery could be happen after first couple of months. And after 6 months, maybe I argue, well, I want a history map of water production. And this way I can adjust the relative permeability to get a better match on the profile. Hopefully everybody were able to follow. If not, please let us know so we can help you with those. Also, let's do the same exercise in the numerical model. So if I click on export button here, what it does is basically take all of these parameters and seed it into the well information card, relative permeability card, and fluid initialization card into the numerical model. So click on export and say yes. So we get into this interface. So we automatically are moved to the numerical model. So you can see in the numerical model, if I want to start with the numerical model, I have to go here and adjust all of these parameters and do many different iterations to come up with a good history match results. But using the numerical RTA will get you here almost 70% of the way. So highly recommended to start with the numerical RTA to get an idea about the performance of the wellbore as well as relative permeability. And you can see in the relative permeability, I adjusted the critical water saturation to 10%. So it is automatically seeded here. Click on save. I can also run this model to come up with this history match, which is very acceptable history match actually. So this is the strength of coupling numerical RTA with a numerical model, and you see on the cumulative basis. Also, I'm under predicting oil. I can adjust for that many different ways. And on the bottom hole pressure profile, you see the spread of the water, the well bottom hole pressure using different correlations. So this is also good match on the well bottom hole pressure. So, and also the simulated versus historical data on the waterfront. You can see that I can still elevate the simulated result, the model results, by increasing the parameter in such a way that I can get a good result, a better result, better history match results on the water as well. So this is the first example that to get to know the interface, which area we're going to focus more. And let's proceed with the rest of the examples here. So the other piece I'm going to cover, and after grid refinement, we're going to have a 10 minutes break. So it's the main important part of these is also grid refinement. Grids are basically the building blocks of reservoir simulation. We discretize the reservoir into a smaller grid block, and we solve conservation of mass equation on each of these individual grid blocks, and then we let them talk to each other. How much mass is coming from one grid block to another block, and eventually, if we have 1,000 grid blocks, we're going to solve them simultaneously, and the wellbore gonna define some boundary condition for our system of grid block, and this is how the wellbore is connected to the grids, and they are communicating, and so we can imagine how many grid blocks, how many phases, how many time steps, how many equations should be solved. And we're going to set some convergence number for solutions solving these equations all together. So that's why it is an approximate solution to an exact problem. Some of the cases, the reservoir simulation cannot converge on the solution. That's where the convergence issue pops up. And there are some recommendations for those as well. And some cases, which are those are could be corner cases where the reservoir is so volatile, it's mostly volatile oil or gas condensate. Still, with a good grid refinements, the reservoir simulation has hard time to converge on the solution. Those cases, you need to contact us to ask for our mastermind to help us resolve those issues. But I'm going to talk about the grid refinement. There are different levels of grid refinement, and they are fundamental to any reservoir simulation. If you set it to higher, it determines the stability as well as the accuracy and as well as the computational cost. Higher grid block comes at the higher cost as well. And definitely poor gridding also could be a misleading result. So we're going to have an example here. I'm going to show you what does poor grading can impact the result eventually. And there is a trade-off. There's always a trade-off. In real life, there are trade-off. In numerical simulation, there are also trade-off. Finer grids also improve the accuracy at the higher cost. So we need to find a balance between accuracy and practicality of the solution. This is the grading scheme that we have in Whitson, and to give you an idea, so how does it work? Basically, the user cannot adjust. The only user or the only option that the user have access to is to set the refinement and resolution of this grid block in our quartile fracture that we are modeling. So these gray blocks represent the fracture, and here we use a uniform grading to see the changes of the pressure and saturation, and beyond the tip of fracture is using logarithmically. So all the changes that happening is mostly in this area. That's why we use more number of grids to capture the changes of pressure and saturation in this area. And the user has only these options: very low, low, medium, high, very high. If you're interested on how many grid block we are using for each of these, I can show you how you can access those information. And so in this example, we're going to do one example together. And this is the intent of the example is to compare the grid refinement strategies in forecasting a gas condensate or volatile. It doesn't matter. So we're going to work together using this example, but I'm going to show the result first. So this is a gas condensate well, and this is the simulated bottom hole pressure. So I'm using bottom hole pressure to predict the rates. So the bottom hole pressure declining and then flat. And most interestingly, I would be able to see using different grid refinement, what would be the oil rate prediction. So as we can see, I set the reservoir simulation to have a flat bottom hole pressure after 400 days. And as you can see, after 400 days here, I'm expecting the rate to decline all the time. But after 800 days, the rate is increasing basically. So there should be something wrong with the number of grid block that I have used. So let's adjust this and use, this is for very low, and use lower grid block. So as a resolution, so with the low, it means that we have more grid with respect to very low. So the profile that I'm getting here is more consistent to my guts for constant bottom hole pressure. I'm expecting the rate to decline. So let's elevate it one more step and use a medium sized, medium gridding. And you can see there's a high discrepancy. By the way, remember this is on the logarithmic scale. So from maybe 5 to 10, this gap maybe looks high, but it's basically a logarithmic. I just purposely use a logarithmic scaling here to highlight the importance of this when we do the forecast. And once we started to use high grid block, they are basically the same. So we need to do this exercise for our fluid, especially if you are in the range of gas condensate or volatile oil, and to make sure what's the level of grading do we need to accommodate to capture the changes of the saturation and pressure effectively. And when I'm using high to very high, there's no more difference. So there is no point of using very high in this case. If I want to use the mic reading, I definitely start with a medium, depending on the application. If I'm going to use the forecast, I'm going to show you the cumulative as well. So on the cumulative, you can see because those changes of discrepancy of the rates are happening at the far end of the life of the well, and those are on the logarithmic. On the cumulative, however, you can see they're not much different. So if you're going to quickly do a forecast study, I would rather use even low or very low to do the forecast, because in terms of the times, despite the fact that we are not talking about hours or days, we are only talking about 1 minute to 2 minutes. But if you're impatient enough to use very high or high, we can also work through very low. So to showcase this example, let's do this example together, and then we're gonna have a quick break here. So for this example, what I want you to do, please, I'm gonna show you, let me grab the example. I was presenting to you the heat map, grid refinement. Okay. So for the grid refinement, let's go to the well section. So in the well section, we're going to add a new well, and we're going to call this well grid refinement. So once you created this well and set the name grid refinement or whatever well you wish to have, click on save, and then it will get you to the PVT. On the PVT section, we're going to adjust the reservoir temperature to 180 and reservoir pressure to 6,000. And for the initial GOR, set it to 3,000. So these are the three parameters. And if you click on save, this is the PVT that you're getting. This is a volatile oil, but it's going to be the same for the gas condensate, because by the time they drop below saturation pressure, they will be very similar in terms of their performance. So once you created these, now go to the numerical model. In the numerical model, I'm going to talk about these parameters later throughout the course. We are not changing anything here. We are just clicking on run. The only thing that we're going to change is to set the grid refinement to very low in our first case and click on run. So if you do so, you can see in a very low, it was like a matter of a couple of seconds to run the simulation. And later, if you get a chance, do the same exercise with very high and compare the simulation. So in this case, we're only modeling 1,000 days of the data. So if you are dealing with the 10,000 data, then the simulation will maybe take a few more seconds. So if you do that, this is the oil rate data. This is the data that I presented to you. And if you want to compare what will happen if you set your grid refinement to a different level, what we can do in order to preserve these results, you can go to the scenario section here and add a new scenario. So in the scenario, add a new scenario. I can set grid refinement to maybe try medium. So hopefully everybody are following medium grid and click on save. So now I'm under scenario of medium, and here adjust the grid refinement to medium and click on run. So you can clearly see it taking a few more seconds to run medium, right? But it was not like a minute, it was maybe 10 seconds. Now we're gonna compare the oil rate forecast prediction for these two cases. And the best place to do that is to go to the comparison plot. In the comparison plot, this is where we basically compare anything and everything that we would like to see. And in a comparison plot, click on add, and the well that we are interested to see is a grid refinement. So select this grid refinement. You can deselect all the wells. If you have thousands of the wells, automatically they are all selected. So we can deselect them and select grid refinement, and you can also set a name to that. We're gonna call grid refinement. You can also access type is there are many different options here that I won't go through all of them. So add plot, and once we add plot, this interface will show up. You can click on edit. So we're gonna see simulated oil rate, right? This is what we are interested to see. So type in here on the y-axis sim oil rate. The numerical model, this is where we created our model, our data, simulated oil rate. So show up here. You can add as many attributes as you wish. On the x-axis, time is a default selection. So y-axis is simulated oil rate, x-axis is time. Click on save. Nothing show up. I have to select my wells, right? In the main, remember it was, if you remember, it was very low, and medium, it is low. So that's the difference between the two. So we may proceed with another example and make it high and compare that high with the medium. And that gives you a very good idea where you need to set your grid refinement. This example that I selected, I purposely selected to be a volatile oil. For dry gas reservoir, for wet gas reservoir, or for even for black oil reservoir, the difference between this much of oil prediction using different grid refinement are not much pronounced as we see here. So this is the idea. So I guess we all deserve a 10-minute break. So if you have any question, you may open your mic and speak up, please. If not, I encourage everybody to take a 10-minute break, please. So we may get back here 10:20, if that's fine with you. Sounds good. You can see from the chat, some of you folks apparently have some technical problem with unmuting yourself. Unfortunately, this is out of my control, but there's no worries here. You can always reach out and we can schedule a meeting later, and we can discuss. We can have any question that you might have. I'm going to quickly highlight another nice feature that we have here. I often use this feature. I'm going to introduce this feature to you as well. This is, so you simulate it, you only see the profile of the only thing, the data information that you receive is the rate profile, gas and on the rate, water and oil, as well as the bottom hole pressure. But if you're interested to see how the pressure propagate into the reservoir and how the saturation are adjusting themselves or changing in the model, you may activate one feature. So if you go for the same example, I'm going to show that for the same example in the numerical model. And there's one button here that says a 2D map. It is set to off. It is basically where the visualization come. You can activate the visualization if you click on that one. It asks you by selecting on this one, if you turn on the 2D map, you're going to relaunch the simulation. So we're going to set it to turn on and then turn on and relaunch. So if you do that, it's basically rerunning the simulation, and this time is collecting the pressure and saturation information and will be displayed to us. So now those information are available. So if you click on the 2D map, and you see those fractures. So by default, 10s of those fractures are selected. In terms of the option that we have here, we can view them from the bird's eye view or side view. And the what attribute would you like to see is the pressure and different saturations. And if you're gonna toggle between dates and date, you can also adjust the color ball, so there's some functionality. And to just for the sake of computational time, we only display 10 snap point in time. So to see, for instance, what happened after 50 days. So you have the option only to see first day and 112 day. So this is how it works. So at the end of the history, you can see clearly deplete in between the fractures, but away from the fracture, the initial pressure was set to 6,000, but now it is close to 6,000. So you barely deplete after 3 years of production. You barely deplete any flow from the boundaries of the wellbore. So this is a great starting tool to also introduce the well spacing optimization using numerical simulation, right? So we're gonna set the well spacing to different level and see how much depletion is happening at the boundaries of this reservoir. And I have one dedicated example to highlight that as well. So this is with the capability to see the 2D map. And let's go to the well control. And the well control, first of all, what does that mean? So how I explain the building block of any numerical simulation is first of all is a grid block, and now it is connected to a wellbore. So the wellbore is basically the boundary condition for solving all of those equations. So with well control, we are defining the boundary condition. What does boundary condition could be available? So these are the well control that are sitting, it's highlighted here, and there are 4 of them: oil, gas, water, and bottom hole pressure. So we also receive a lot of questions. What's the best practices to set? What's the best well control that we need to pick? Is it oil, gas, water, or bottom hole pressure? So the argument would be definitely on the fluid type that you are dealing with. So these are the definition of the constraint: oil, gas, water, and also we have a liquid. By liquid is set the let me take the laser pointer. So oil is setting the oil production rate, which is my preference if it is I'm dealing with the oil reservoir, because this is the commodity that I correctly do the measurements on. Therefore, I want to honor that in terms of the material balance and how much fluid I withdraw from the reservoir. I tend to work with the oil as my constraint. But I can also use the bottom hole pressure to predict the oil. So if I'm selecting oil, I'm using oil information production data to predict the gas, water, and bottom hole pressure. If I'm selecting bottom hole pressure to be my well control, I'm using bottom hole information to predict the rest of the phases. But you could see in the one, specifically in the case that I'm predicting the bottom hole pressure from the surface information, this is the caveat. This is the case where we have the spread of bottom hole pressure prediction. So which bottom hole pressure would you like to choose for predicting the rate? So this is where uncertainty comes into play. And with different bottom hole pressure, you may have different production rate. So we're going to have some examples and toggle between this well control to come up with what would be the impact. But a good history match practice would, if you select oil to predict the bottom hole pressure, depending the bottom hole pressure data are trustworthy and you have some good confidence in those, maybe you have a gauge data and use those gauge information to calculate the bottom hole pressure to the top perforation. And you can imagine in the 4-mile lateral length of the wellbore, these days people are drilling, we only have one representative bottom hole pressure, which is the bottom hole pressure at the top perforation. The rule of thumb for the lateral length per 1 mile, there are 100 psi pressure difference. So from the toe to hill, there could be up to 400 psi pressure difference, which is still another, this is how we simplify things, right? So let's see each of these well control. So this is where I'm selecting oil rate to predict the rest of the phases: gas, water, and bottom hole pressure. This is not intended to be presented as a good history match results. This is simply showcasing if I'm using oil rate to predict the rest of the phases as well as bottom hole pressure, what the result I'm expecting. And second one, I'm using gas rate to predict the rest of the phases. In the oil reservoir, I'm expecting to use the gas to use the oil to predict the gas, not the gas to predict the oil. But in a gas condensate, where the primary phase is the gas and oil is mainly coming from condensation of the gas on the surface, I would rather use gas to be my well control and predict the rest of that. And this case, I'm using water rate. You may argue, well, there are a lot of controversial discussion about the water, the accuracy of water measurement, specifically with the rate allocation and uncertainty in the measurement of the water. I may not use the water rate to predict the rest of the phases, but there are some special cases. For instance, if you're producing from an aquifer, this is the only phase that you're producing, so you would rather use the water rate to predict the pressure, bottom hole pressure. In those cases, you're not producing any hydrocarbon, therefore the capability is there if you're dealing with those aquifer. And finally, you may use well information to predict the rest of the day. So in this special case, you can see while honoring all the spike in the bottom hole pressure, you get a lot of discontinuity in the rate prediction. So the recommended practice, if you are using bottom hole pressure to predict the rest of the phases, is to at least smooth the bottom hole pressure. I'm going to show you quickly how the smoothing works. One example for this one on the same well that we work together. If you can please go to the valve, the kite valve. So these fields, all of the fields that you can see here are searchable. So the valve that we adjusted the critical water saturation, its name was kite. So if you start typing kite, they will show up and you can click on that. So if you go to kite, this is the history match that we got. If you go to the bottom hole pressure, in this case, the bottom hole pressure, you see, let's use bottom hole pressure to predict the rest of the phases. So I'm going to use bottom hole pressure. I'm going to set time stepping to a smart. So there's all custom. I'm going to select a smart. And grid refinement, I'm happy with low. So selecting well control to be PHP, run it and see when I run all of these. So you see, it is selected to be a smart. If I select it to be all, let's quickly run with the all and see if I can see those spike in the rate or not. So you see all of these spike. This is basically non-reservoir effect. This is simply because suddenly I know this is the wellbore effect. This is not the reservoir effect. So I have to disregard these. I shouldn't include this as a boundary condition to my valve to predict the rate, because this is kind of not realistic scenario. So in order, if I'm very motivated to use the well control to be bottom hole pressure and not deal with this scenario, the best approach, recommended approach would be to go to BHP, and in the BHP plot, this is all the correlation that we had and took a look at that. And I'm gonna customize my bottom hole pressure. So click on this drop down and customize custom PWF and custom PWF. When you select on the custom PWF, this window will show up. And we're gonna do some smoothing functionality in our software to smooth this data and basically disregard all of these spikes. I know this spike are the artifact of the wellbore effect. These are not the reservoir effect. And it's very important to identify the wellbore effect and exclude it from our analysis, because all the analysis that we're going to do is on the reservoir effect. So there are many different functionality here. The one that I'm very comfortable with is this. I'm going to show you that quickly here. If you select the sample frequency, maybe to 5, and simply click on, so select sample frequency to 5 and click on autofit. It goes through this data and select the 5th data point and connect it linearly to each other. So this is how it smooths the data. So instead of dealing with these outliers, they're simply dealing with this. And in terms of the functionality, if you click on this and you will argue, well, this data is not representative at all. So you're gonna grab it. And so, sorry, it didn't show up here. I guess I have to put it here. It was working on the version that I was dealing. Okay, so if you throw it outside of the chart, it will disappear. So here it doesn't work. You need to put it here, simply connecting these two lines. So you may argue, for some portion of the data, we run the gauges in the wellbore. Therefore, we believe those data are real reservoir effect. I'm going to use, instead of frequency of 5, I'm going to use frequency of 1. So let's imagine, we're going to zoom on this data set. So imagine this part of the data is reservoir effect. So I'm gonna, instead of frequency of 5, I'm gonna use frequency of 1. So I'm gonna adjust it to 1, and then this functionality here, there's a lasso feed append. lasso feed append. This is fourth in the fourth option here. So if you click on that one and lasso feed those data that you believe are trustworthy, you're gonna honor all of those data, right? You're gonna honor all of those data with a frequency of 1. So I'm gonna revert it back to 5, or you may argue, well, this portion of the data, I have the least confidence in these data. So instead of frequency of 5, I'm gonna use higher frequency, lower frequency basically. So I'm gonna append it again, lasso feed append, and I select them. And this time you see less resolution on the data, right? So there are a lot of other functionality, remove, include, etc. If you want to add points, you can easily add 1 point to get higher resolution. So select add points and add it here. So point is added here. So this all of this information, although available, if you want to present it in other software or present it in Excel. So these are the data. I can clearly see this dip is not a real reservoir effect. Or maybe I have to consult my production data and see if actually there is a higher production rate here that causes this dip here. So let's click on save. So now I'm using a custom PWF that's highlighted by yellow here. And in a numerical model, I'm going to rerun this one, this time with the new bottom hole pressure profile. And as you see, I'm expecting much better result on the oil and rate profile. So there is still some spike in the oil rate going to 0. This could be attributed to, so we need to adjust those bottom hole pressure in order to get a better match of this. All good. So this is about the well control, smoothing functionality, and this is the example that we presented. There is very nice functionality, which is this bottom hole synthetic. It's a lot of use, and not for the history matching, but basically for creating all the synthetic cases. So this morning I was working with a client that they were comparing the performance of a shale gas, which was adsorption was activated versus a free gas. So this option on the bottom hole pressure profile, synthetic case, is very useful, and I'm going to demonstrate the capability and how you may use to your advantage. So when you open the card, so if I go to the bottom hole pressure and on the well control, I adjusted the bottom hole synthetic. These are the options that shows up. Let me quickly walk you through these options and what are each of these mean. So this is the well bottom hole control. When I activate it, then if I generate the production rate, this is what will show up on the oil rate versus the bottom hole pressure. So this is the minimum bottom hole pressure that I adjust. So the bottom hole pressure, once reached to this point, they're gonna stay flat. The time to minimum bottom hole pressure is set to 50. So how quickly I introduce my decline, in this case, it is 50. The total simulation days is 3,000 days, or rate constraint type. So imagine there are some surface facility constraint that only can accommodate 1,000 barrels of oil per day. And plus some producing water. Therefore, I'm going to set the constraint for the oil rate to be 1,000. So it's cap at 1,000. And once the reservoir bottom hole pressure reach to 1,000 psi, then the bottom hole pressure stay at 1,000 and rate is start to decline. And so this is rate constraint 1,000. Rate cutoff is also indicating that what's the abandonment condition. So we have different rate cutoff, oil, water, and gas. So in this case, I set it to be 20 STB per day. So once we get to 20 STB per day, the simulation discontinue. If it's happening before 3,000 days, so we will discontinue. So let's proceed with an example here. So in this case, we have different oil constraint as well as different rate cutoff as well. Okay, so there is one option. This is the export option. I'm going to do one exercise together to also introduce this export option. And this is great tools for simulating some synthetic cases and also doing some sensitivity analysis. So let's go through this example as well. So I'm going to generate the synthetic production data. And with my synthetic production data, and let's get some of the parameters here available to me. Synthetic production data, perfect. Okay, so if it goes to wells section, we're gonna add an example, call it synthetic, and click on save. And in the PBT section, we need to set the PBT for our synthetic case. Keep reservoir temperature 2000. For the reservoir pressure, drop it to 6,000, please. And initial GOR is 1,000, should be okay. And click on save. And this is the PBT that we generated. And if you are interested in other information, these are the information summarized here. Now go to the numerical model. And in the numerical model, these are some of the parameters. So leave them as is. Click on save. And for the grid refinement, low is fine. This is the controls on the well control. We talked about that. It's set to bottom hole synthetic. And these are some of the parameters that goes into the bottom hole pressure. And what I want you to do, please also click on the 2D map. So we have an idea of how the pressure propagates into the reservoir. Turn it on and turn on launch. So it's running, shouldn't take that much. So it's our data. So this is what is forecasted, right? But what I'm interested to see, set this forecast data as my production history. And that option is in the export button. So if you click on export, and on the very bottom, there's a set historical data equal to the simulated data. There's two options, set historical bottom hole pressure to the simulated bottom hole pressure. But this set historical data to the simulated data, click on that one, please. And it say, okay, if you click on that one, the data production data will be overwritten, and we want to do that. Click on yes. Just take a few seconds to set the forecast to production data. So in this case, we created a model using this information that we know the answer already to generate these production data. Now we're going to do some analysis on this production data, assuming that this production data are the real well production data. So let's do some flowing material balance on this well. If we're going to do flowing material balance, we can go to the flowing material balance. We know that this giving us an estimate of contacted fluid in place. So clicking on the flowing material balance and click on run. So in the production data, if you quickly go to the production data, this is the information that I generated in numerical simulation, right? It's very similar to actual production history. So I'll go to the flowing material balance and click on run. So it's running the simulation data. And we know from the flowing material balance, I'm going to select a trend where it's stabilized. This is apparently my trend. I'm going to use this data to predict the volume of the reservoir. So there's some functionality here. Fit option. If you click on this row, and there's a spray gun fit. Spray gun fit will allow me to select the data that I can visually see there's a trend here. So clicking on this data, to adjust the size of the circle, you can use your middle mouse and selecting the data, select the data point that you would like to draw the line through. So by clicking on that one, now you're calculating also bottom hole pressure. So bottom hole pressure bottom hole pressure has been inputted, the average reservoir pressure. So using this technique, my analysis is telling me that so far I have contacted 3.5 million STB of gas. Let's go to the numerical model and see how much I inputted based on the dimension of the reservoir, right? Numerical model. What I inputted is close to 7 million. So 7 million versus 3.2 million is almost half of the way. So I'm predicting contacted oil in place to be almost half of original oil in place, which is very disappointing. And the reason for that is maybe I haven't contacted all the boundaries in the reservoir. That's why I ask you before running the case, click on this 2D map. Let's go ahead and see how the pressure is propagating into the reservoir. So here is the layout of the wellbore, and I gotta advance through this one and see, well, the fractures start to interfere. Let's make it day after 112 days and after 570 days. All the region in between the fracture are very depleted. So this is the color bar, and after 1,000 days, there's barely any depletion from the edge of the reservoir, right? So fluid material balance doesn't see any of these portions of the fluid in place. In order to see that, I can do two things. Maybe run the simulation for an extended period of time instead of 1,000 days, maybe 5,000 days, to effectively deplete this portion of the reservoir, or make the boundary of the reservoir smaller. So in this case, I'm going to close on this one, and a very simple adjustment would be, instead of 8, so we see the fracture half length is set to be 400, reservoir half length is set to be to 800. So what I gotta do, I gotta click on this one, use XE equal to XF. Once you do that, you see the fracture extended all the way to the edge of the boundary. So click on save, and now run the model one more time. Hopefully my pace is okay. If not, please somebody let me know I'm not checking chat more often, which I believe I have to. So now I generated another sets of production data. And you can clearly see because this is logarithmic, the difference are not very obvious. So I'm gonna export it one more time, the new data as the simulated data, and click yes. So in this case, the OOIP, they're up to 3.5 million. So I almost truncate half of the reservoir. Initially it was 7, now it is 3.5. So let's see what fluid material balance is. See, I'll go to the fluid material balance using updated production data and see, you can also adjust the slope to be this one, maybe, right? And run to get the bottom hole pressure as well. In this case, it's predicting 3.3, right? What I feed into the numerical model is 3.5. So I'm getting there almost 95% of the way. So this is how you can generate any synthetic data that you wish. And my recommendation would be ask your colleague or your friend to generate this data and pass it to you as a well production data, so you're not biased towards the answer, and do the analysis yourself. This is the best way that you can learn about any parameter in a numerical simulation, or you're going to test some ideas. This is the only way that you can generate these synthetic data. And remember, these are the synthetic data. If your analysis are wrong, why I would say 10%, it's okay. Well, with the actual production data, you should be expecting a lot of noise on this data. So sometimes the trend is lost. So you should use your experience, and you can also layer in another noisy level of noisiness to this data. So it's look like resemble more representative of what on the daily basis you are dealing with, and do the analysis towards that. So this is very nice, nice capability of the software, functionality of the software that I personally really enjoy using that, and to showcase some of the conceptual question that we are coming across through using this synthetic data. So at the end of the day, these are all the list of the parameters that you are given the chance to adjust, right? And pretty much for all of them, you have some degree of uncertainty. For the initial reservoir pressure, depending if you have any defeat information, or especially if you are analyzing an offset valve, which we have been some production happening from the valves, and what's the representative initial reservoir pressure that well describe the initial reservoir pressure in your parent valve, in your child valve. Matrix permeability, you can do some analysis, but there are huge also uncertainty in the porosity, fracture conductivity, gamma, barely any test on the true confinement stress regime that represent the reservoir to come up with what is the true fracture gamma and matrix gamma. Rock compressibility, we use correlations, a little bit underestimate for high pressure, but you need to increase it maybe a factor of 3, might be a factor of 4. Reservoir height and reservoir fracture, if you're lucky, you have some reservoir fracture modeling technique that you're going to use to give an estimate of that, or some monitoring, seismic monitoring, microseismic information. Lateral length, you know how much you drill because you pay for that, right? Half length, it could be, we are using one representative half length as a representation of all the maybe 600 fractures that we put in the reservoir. Number of fractures, another degree of uncertainty. Relative permeability, nobody knows, but we know the workflow, right? Fluid initialization, hopefully we have some good resolution data to start with the representative GOR of the reservoir. Water saturation, talk to the geologist. Sometimes, yeah. So these are all the knobs that you can turn. But if your knobs, your turn is so high, they will confess to anything. So we need to be very careful. At least keep the consistency between these parameters. So with the relative permeability recommendation practice is come up with a set of relative permeability and then apply it to all the wells in the same region. So that's type relative permeability instead of type well. We use representative relative permeability. So what's a good history match? A good history match is that it can replicate the production data with the level of uncertainty that we believe it is. What do you want to use as a well control? Is it oil rate, water rate? For the oil reservoir, it makes sense to use oil rate. For the if you have some confidence on the gauge information, bottom hole gauges, you're welcome to use those. If you toggle between well control and oil rate to predict the rest of the parameters, they should be consistent. The parameter should be meaningful. You cannot use excess of 1,000 for the well spacing of 800, right? Unless you have done a very aggressive job of completion stimulation. So your effective fracture half length is beyond the well spacing. If it is predictive, it should be also descriptive, and also, so these are high level definitions of what's a good history match practice. So I call this one a good history match practice. We're going to work through one example that's basically using this data. And we're going to toggle between different bottom hole and oil rate control to predict the rest of them and see there's some consistency between those. And on the cumulative basis, it's also important to note that your cumulative is expected to be between 5 to 10% at the end of the history. So at the end of good history, not 100 days of production data is not a good amount of history. At least you need 6 months production data or to 1 year production data to be able to have a good confidence in your history match model. You're expecting to get to the cumulative within 5 to 10%. You're expected to also follow the trend of the data. So is the slope, you can have the endpoints that match perfectly, but they are on the different slope. So it's not acceptable. On the GOR, we know the GOR is a cloud of the data. At least we need to also make sure that the trend is captured. On the water-ore ratio, we already talked about the water-ore ratio. What part of the data did we need to put more emphasis and more weight on, and what part of the data is basically the true reservoir effect that's we are producing from. And this is so once we are with this one, there's also report the error on our history match, right? This description of this realization of the reservoir and fracture properties with these sets of relative permeability during the history of 1,000 days, it gives me a 13% error. In the manual, it is mentioned how this error is calculated, but 13% is very well qualified to be called as a good history match model. So we also have some options. So this option is basically setting weights for some of these for the portion of the data. If I believe that towards the end of production life of the well is started to experience some loading effect. So those bottom hole pressure calculations are basically in not correct one. So we can simply disregard those and we can ignore them. And the way that we ignore them to report this current history match error is to set weight equal to 0 for those. But if you have some portion of the data that you are confident this is you need to honor them, you can set the weight for them to be higher than 0, higher than 1, and the maximum is set to be 10. This is all theory, but let's say in theory, there is no difference between theory and practice. In practice, definitely there is. So it's really important to also, before doing any of these, you need to validate some basic parameter, where the PVT is coming from, the bottom hole pressure like we discussed. It's really important to differentiate between wellbore effect and reservoir, because we do the analysis on the reservoir part. We need to understand the wellbore part as well, because they are working together, and what's getting produced on the surface is a combined effect of all of those. So we need to set aside wellbore effect and focus on the reservoir effect. And also, it's really important to integrate all of the data that we have, not only the well production data, but any offset operation that happened, right? To see what the real reservoir effect. So these are some of the key highlights from these. And let's go to a dry gas example and do a history matching and see. I'm going to show you how quickly we can come with the history matching of a gas well. And then we have an oil well. We're going to do the same. We're going to history match oil and water production. And then we're going to focus on the forecast. So for now, let's go ahead and please on the wells that we inputted. One of these wells is the Pheasant well. You can type it here as well. Is a dry gas well. We're going to quickly take a look at the production data. So if you can go please to the dry gas. And the first thing first, we need to set the PVT. So if we go to the PVT section and click on the edit properties, reservoir fluid composition, and on the drop-down list, as the GOR is set, now set it to dry gas. If you set it to dry gas, gas specific gravity is set to be 65.65, specific gravity of gas, and click on save. So the PVT is generated. You see the initial reservoir pressure and temperature, and separator pressure and temperature. So this trajectory, we don't cross the phase envelope. That's why no phase is drop out of the solution. So on the bottom hole pressure, This is the gauge bottom hole pressure that comes with the data. This is SP repository. Calculate bottom hole pressure. With this wellbore configuration, you see how closely the different correlation from bottom hole pressure are clustered because this is dry gas, because this is less multi-phase effect is going on here. So regardless of whatever bottom hole pressure I'm selecting, the difference between these two different bottom hole pressures in the order of 50 psi, which is I can trust my bottom hole pressure in this case. Again, highlighting the importance of checking on the data before doing an analysis. This is on the liquid loading plot. This is a gas rate versus the Turner rate. You see there's a very good gap between the two, indicating that the well is not suffering from the liquid loading, but towards the end of production, even not looking at the Turner rate, you can see the data get very sporadic. And this is a good sign that the liquid loading is happening in the wellbore. You see all the spike and all the rates decreasing. So suddenly is an indication of the liquid loading. So we may put less weight on this portion of the data, right? So bottom hole pressure, PVT. Now let's go to analytical RTA. Because if I go directly to the numerical, if I go directly to the numerical model, now I need to deal with all of these parameters all at the same time and turning them and adjusting them to get a good match. But see how quickly it would be to start with a numerical RTA. Click on Run. And you see the cumulative is there. This is the water gas ratio because there is no oil production here. Simply adjusting this line, I'm able to set the cumulative, right? So this is a great starting point. You see, only I'm adjusting one line and coming with the history match parameters, one realization for history match parameters. And then I can export these, but it will be also insightful. We cover a whole course on the numerical RTA, the best practices. But I would rather also take a look at the rate as well. And as you can see, these are the rate. So the early time, I know there are a lot of cleanup happening, and could be finite conductivity, could be anything. But you can see when I'm adjusting these lines, I can either history match the late time, I get a mismatch on the early time, or I can history match the early time and get a mismatch on the late one. This is a very good indication that maybe the pressure dependent permeability is the case here. So I'm gonna quickly adjust those parameters because it's an enhanced numerical model. We also have access to those. So maybe adjusting those to 2 as a starting point, because I clearly don't have any idea about the fracture gamma and matrix gamma. But similar to relative permeability case, if I started using for one well in the area, it makes much more sense to also adjust them for the rest of the wells. But the best practice is to come up with an idea for the matrix gamma and fracture gamma is once you have drawdown and build up. The build up gonna tell you a lot whole story than the drawdown itself. So focusing on build up and drawdown give you much more confidence in determining if there is some fracture conductivity degradation or pressure dependent permeability. So all of those parameters, fractures, matrix, gamma, as well as the FCD, right? FCD also telling you some story about the pressure drop in the fractures. There is no way and that you can decouple them, all of them working together, right? And so it's important to have some workflow developed. Those workflow definitely include having drawdown and build up. So let's see, adjusting these two and setting, running the model. Now, let's see if I click on this one, you can see it's getting much better. Not much better, but it's definitely early time is better. Late time is also I'm settling on the data. So let's export this data, and yes. So click on run. Let's use gas rate to predict the bottom hole pressure. And I'm using the smart time stepping with low grid refinement. And this is the first pass of relative permeability, the first pass of bottom hole pressure prediction. I know it is off. Now I can do some adjustment here. The first adjustment that I can have, let's see what parameter do I get here. So the matrix permeability close to 30 nanodarcy, and fracture half length 1100. It's a little bit on the high side. We don't have any information about the design of these compilation and also the estimation, how much they injected, the load recovery, as well as the fluid they injected to complete these wells. we don't have any idea about the well spacing. So in those sense, we are blind. But if we want to do our best in order to history match, we can increase this 30 to, let's say, 40 and come up with how we are predicting on the bottom hole. So now it's much better. So I can settle on maybe 30, 37, I would say, and run it. Let's see how quickly we can settle on the bottom hole pressure. And sometimes you need to expand this plot to have a better visualization. You can see early time is under predicting, late time is over predicting. But if you shrink it, and it's really good. So don't get fooled with the scale of the plot. Always do focus on the part of these. So this is one period of drawdown plus one period of build up. You see how nicely it is building up, right? At least I'm honoring this data. So the more of this data, there's almost a period of 8 days of build up, and this gives me a very good idea about maybe I'm setting my gamma parameters nicely here. So if you have multiple builds up data, you can take advantage of them by focusing on this build up behavior. We history match this parameter, but remember, you may argue, why did we started with increasing permeability? Maybe I put it set 30 and run it again, and now the model's under predicting. What I'm gonna do, and instead of matrix permeability, I'm gonna drop XF, right? I'm gonna drop it to 1000 and see. Sorry, I have to increase it. Maybe 12,000, 1200, and run it. So now it's getting a better match towards the end of that, or maybe there's no fracture conductivity. There is no fracture and matrix gamma. I'm gonna set them to 0, both of them. Or because this is high, I'm gonna, instead of 4, I'm gonna make it 8. These are all the possible realization, right? We never know about the uncertainty. Now early time is good, late time and I had to drop it. Now, okay, what about FCD? It's 1000, maybe it is 400. We never know, right? And run it. So I'm living in the world of uncertainty. All of this stuff is really uncertain. Therefore, there is one tab dedicated to dealing with the uncertainty, how to deal with the range of possible solution. That all of them can give me a good history match results, acceptable history match result, but the forecast may be totally different. That's where probability comes into place, and P10 and P50, P90 come into place. So we're gonna touch base on that as well. So maybe we continue for another 10 minutes, and then we have another 10 minutes break. So another integrated part of this numerical model is when we history match, and you remember the goal of reservoir engineer, or come up with a reserve, OIP, an OGIP, and then be able to forecast. So in the forecast, what forecast do we need? So this tab is over here, include the forecast in the numerical model. And there are many different capability in the forecast page. I'm gonna present a couple of them to you through some examples. Maybe we use the examples for the dry gas. Okay, so there was, before going to the forecast, I also wanted to present you this kite fall history match that we did together. So if you can go, please, to the kite wall. So we can go in the wall section, click on kite. The kite shows up. So this is the first history match result that I get, right? Which is not too bad, actually. On the cumulative, I'm under predicting both oil and gas, so I can adjust some of these parameters and to get a better match. Let's go to the starting point for this one would be the numerical model. So for the numerical model, with the grid refinement, you see for the numerical model also, we are using a grid refinement to be low. This is a great starting point, and I'm gonna give you some idea. So we already adjusted the relative permeability to be 10 on the GOR. So on the GOR, we are in the ballpark, but not very great. So maybe we go to the numerical model. And in the numerical model, so we're gonna make this history match a little bit better, right? So first thing first, remember we did a smoothing on the bottom hole pressure profile, and let's go to the well and reservoir data. And on the well reservoir data, I have one set of parameters that I would like all of us to include those. So we see how how the result of history match look like. So for the number of fractures, this is coming from the SPE repository. So we don't know how it is completed. What they inputted here is 306, which is simply calculated, the way it is calculated is number of cluster per stage times number of stages. So this is the total clusters that we put, and they believe it is effective. That's why it is not enough. It's said to be 360. I'm gonna go to with the 50% of that, so I'm gonna set it to 150. And the height of the reservoir is 56. We're gonna leave it as is. On the XF, I'm gonna put it 265. And for permeability, I'm gonna put it 48. And these two are let them to be toggled on. So this indicate that fracture, hydraulic fracture is basically the height of the hydraulic fracture is the height of the reservoir. And there is no flow from beyond tip of fracture. So XF is basically our XE in this case. And click on save. And on the relative permeability, this is 5. Maybe lower it a little bit, make it 4, please. This is 2, make it 2.2, 2.2. And on the matrix relative permeability to gas point, leave it 0.8. So 4, 2.2, 0.8. Click on save. So this is what we ended up. And no. And on the constraint, it is, let's set it to oil, because this is oil reservoir. Okay, so with the oil reservoir, let's turn it to the oil rate. And remember, this is a log, semi-log plot. And maybe it really look nice on the gas profile, but what you need to do, you need to expand it. And you see at least some of the portion of the data I really nailing on the history map, right? I'm getting the trend towards the end of production data. Early time, yeah, I believe this part we can have a better representative of relative permeability. So we need to argue at this point, okay, has been any operational changes in nearby or not? Or is it all the reservoir effect from the well that we are analyzing? So these are some external information that we need to put into our history matching practice in order to make it better. And remember, this is for the well. We're only representing all of our production data with a quarter of fraction, right? On the water, yes, the early time is the early time definitely on mismatch, and we don't care about this much. But towards the end of production, definitely nailing on that. On the bottom hole pressure, remember this is the oil well. We have some spread of bottom hole pressure up to 1,000 psi. With 1,000 psi, at least I'm getting the trend. Okay, right? And for the or water, or it's for the GOR profile. This is the part that we didn't did a good match on the GOR, and but towards the end of the production, at least I'm getting the trend. Okay, similarly with the water cut. So the cumulative, let's take a look at the cumulative. I'm studying this. I'm expecting this to be correct. So for this one, not too bad. Maybe I can do a better job on this one. And yeah, so this is kind of history map, the first realization, but there could be many different realizations which could be addressed and communicated through the probabilistic. All good, let's proceed. And this is the kite flow, or do the forecast. So for the forecast, let's quickly show you what does each of these parameter means. So this is this is the history part. Now we're gonna forecast. So we have some idea of how the pressure will decline. The first pass would be the pressure will decline as it used to decline before we started to forecast. And then we're gonna set to some start date. What's the start date? This is the end of history. And we can also have some option. I'm going to show you what are these options means for last simulated bottom hole pressures. It's basically it's telling us the where this first date and first bottom hole pressure for the forecast period will start. And then if we have a rate cutoff, this is very similar to bottom hole pressure synthetic that I presented to you. We can set a rate cutoff for oil, gas, or water. And then if those rates are drop below those rates, the simulation is terminated. because they achieve the abandonment condition. And we also have some information on the decline. How quickly do you want to decline the bottom hole pressure? And there we can introduce many different segments into your forecast. So some of them could be very gentle. Then your facility can handle extra rate. Therefore, you're going to draw down it more aggressively and at a higher decline rate. So we can set the decline, different profile. This is hyperbolic, and this is a linear and a connected another set of hyperbolic. So there are a lot of functionality for the forecasting. And eventually you can also run different forecast profile as a sensitivity. So we have one example that the one client requested what will be the impact of drawdown strategy on ultimate EUR. And eventually the forecast looked like something like and we're going to practice that forecast. So let's take this kite example and do one forecast to complete history match forecast, and then some examples on the synthetic, how we can forecast from day one, and also how you can generate some shut-in, because it's inevitable to also have shut-in periods during forecast for a month or so. I'm going to show you how you can include those shut-ins into the forecast. And then another part of this, before that, we're going to have a quick break as well. So let's start with the kite valve where we left off. So we're going to include the forecast. If you click on the include the forecast, and then there is an edit forecast schedule. So this is how forecasts look like. So you can zoom in here to see the end of the history, and if the forecasts are connected automatically, the software will select the end of the history, last simulated bottom hole pressure, and for last data point. But you are welcome to adjust this. Imagine that you're gonna have forecast at 1050, right? You can set it to 1050, and you see the forecast is back extended all the way to 1050. But we're going to leave it to 66. This is the profile of the forecast is controlled by this parameter. How long do you want to run your forecast? It is automatically set to 10 years. So we're going to set it to maybe 1500 just for the sake of time. Okay, let me save it. For some reason, my screen is freezed. Let me close the window. Whitson. Okay, I'm gonna search my name. Kite, numerical model, edit forecast schedule. This is my forecast, right? So let's set it to 1500, just for the sake of demonstration, right? And save it and run it. So the time stepping, I set it to all, but I can, despite the fact I set it to all, you can see how quickly it is. So this is how it is forecasted and how the cumulative look like. So it will be very insightful to also compare the result from numerical simulation with the decline curve analysis, right? So you can, there are option in the DCA that you can call the result from numerical simulation forecast and see how those rate profile look like. All good. So this is the forecast. Let's proceed with the another example as let's forecast from day one. So what we can do, we can also, without having any production history, like the synthetic case that we made, please go to the valve, in the valve selection, add another valve and call it forecast to distinguish it from others, and click on save. And for the edit reservoir properties, the edit reservoir properties, you may drop it to 6000 and click on save. This is the phase envelope. This is the black hole PBT and the numerical model. We're gonna set it to x equal to xf just for the sake of simplicity and saving sometimes, not to account for the region beyond tip of fracture, and save it. And if you go to the well control and set it to bottom hole pressure, so in this case, there is no production data. In order to be able to forecast from day one, in the bottom hole synthetic, you got some limited options on the pressure profile. You cannot connect different segments for the forecast. But in order to be able to do those, we switch to the bottom hole pressure and then include forecast. So if you do so bottom hole pressure on the well control, include forecast, edit forecast, right? So as you can see, my forecast starts from day one, and I can set it to day one. I can set it to a specified bottom hole pressure, and how many days, maybe 100 days or 1,000 days. Initial bottom hole pressure is said to be 5,900 because my initial reservoir pressure is 6,000, and this is 20, maybe. Specify bottom hole pressure. Okay. Maybe, okay. Now specify bottom data hole pressure. So let me try one more time here. Okay. Fluid forecast, bottom hole pressure. This is related specify. Maybe I have to select specify bottom hole pressure 5,900. Maybe I can show that through another example. Let me quickly find the other example here. I have the examples on the. I'm gonna get back to this example one more time before I finish the course. But we can definitely forecast from day one, and make sure I present that to you, numerical model and forecast. Okay, so let's proceed. I will get back to this example at the end of the course for sure. So another component to the numerical model is the sensitivity analysis. With the sensitivity analysis, so we're going to study several factors here, right? And it's very clear in terms of how we can access that. It is just beside the history matching. So once we did the history matching, we're going to study the sensitivity analysis. And the intent of history matching and sensitivity analysis is to test how the changes in key input parameters affect the model. So we're going to do sensitivity analysis on different parameters, and some of these parameters are listed here. I will show you one example with the sensitivity analysis, and we also can do a sensitivity analysis on the well control as well. And this is how the interface look like. Let's do one example on the sensitivity after break, and this is some of the tornado plots that we get on the sensitivity, and as well as the bottom hole correction. So the example that I have for you is the client reached out and say we have some evidence that pulling too hard on our oil, on our wells, apparently these are oil wells, and the black oil window, they realize that it's to make the EUR of the wells lower. So how would we best method in Whitson to model that? So this is what we're gonna do right after the break. Maybe we take 8-minute break to be able to also cover the probabilistic. So we'll get back here at maybe 11:26 or 27. And in the meantime, I will work on that two examples, so I will present them to you as well. In the meantime, if you have any question, I would be happy to hear. Otherwise, enjoy your break and see you in 7 minutes. Hopefully everyone enjoyed the break and realized I've been a little bit, my pace was a little bit not a slow down, so we couldn't follow. I'm sorry for that. And but the good point is that the session is recorded, so you will have access to recording, so you can follow up with those. And if you have any questions, we definitely can have separate meetings. I know that there was some inconsistency on muting yourself and speak up. So no, we definitely will reach out to have sessions with you folks. And let's proceed with the rest of the slide. In this part of it, it's almost half an hour, and the half an hour, almost 60 plus people are staying online. So truly appreciate your time. Hopefully we were able to communicate some good content here, and it was informative. But I believe we can have follow-up sessions. So don't hesitate to reach out if you want to have in-depth discussion on some of these content. So the problem that I want to present to you is the problem that was brought up to us through one of our client, and the question was how we can determine if the drawdown strategy that we have for our wells in the oil window impact our well performance EUR of the wells. So we're gonna take advantage of this sensitivity in Whitson and see if we can address that problem or not. So to do that, I'm gonna quickly consult some of my slides in order to see what parameter do we need to have for the sensitivity? Oh, apparently these are already here. So let's go ahead and create a val with these parameters. We go to the val section, please. By the way, I was able to find out the edit forecast from day 1. So this is maybe I had to put this information from day 0. And if I do so and forecast it, was working fine. No, I'm different on the different. I will get back to this. Elena mentioned to me I skipped one of the steps, so maybe I get back to that later. So for this exercise, let's go and add a val and select sensitivity, then drawdown sensitivity, drawdown sensitivity, and split me my PVT. So on the PVT side, click on PVT and set the initial GOR to be 3500, and click on OK. So this is the oil window as we are interested in, and then go to the numerical model. And in the numerical model, we're going to keep everything as is and run it with the bottom synthetic. So this is my base case sensitivity. So in the base case sensitivity, this is my profile. Now I'm gonna investigate what would be the impact of drawdown. This drawdown that I have is for this sets of parameter. So let's go to the sensitivity section. In the sensitivity section, and on the last card here, we have a sensitivity card. Click on the edit sensitivity parameters, and these are all the parameters that we can run sensitivity on. So for instance, if you are interested to see what would be the impact of critical gas saturation on the GOR profile, you simply click on the critical gas saturation and see those information for different sets of critical gas saturation, and the GOR profile will show up. The other piece we are interested, maybe we're gonna do sensitivity analysis on the well performance, like on the well spacing. So for this same value of XF, if I increase my well spacing, how much extra reserve I will be able to produce because my well spacing is set further apart. So, but in this case, I'm interested to do sensitivity analysis, not on the reservoir properties, but on well control. So if you select the well control, my sensitivity analysis, now I'm going to introduce different cases. So case 1, case 2, and case 3. Let's populate this information for different cases. So for case 1, I'm going to draw down at after 400, I'm going to, from the initial reservoir pressure, I'm going to draw down in it after 450 days, which is this information, to 500 psi. 500 psi is this 500 psi. So from initial reservoir pressure all the way to 500 psi after 450 days. In the case 7, so this is case, call it maybe pick a proper descriptive name and say medium. In the second case, which is I'm going to draw it down instead of after 450 days, I'm going to draw it down to 250 days. So after 250 days, from initial reservoir pressure to 500, and this is a little bit more aggressive, right? So for case 2, we're going to call it hard. And case 3, maybe draw it down to after 50 days. So with the 50 days, you see, this is the pressure drawdown from 8,000 to 500 in 50 days. It's a quite very aggressive drawdown. Some case, in this aggressive drawdown, especially if you are in the volatile to gas condensate window, you can see that the numerical simulation doesn't run due to the numerical issues. So because they are introducing huge pressure drawdown as a well boundary condition. So we need to be aware of that, and we're going to see, hopefully we can run these cases all together. We're going to call it aggressive. So with these 3 cases, let's go ahead and next. So these are, we have some options to adjust the line type, line color, and we can also always return back to this page to adjust those parameters. Click on save. Now our 3 cases are generated here, and all we need to do is to click on run. So how quickly it is running for the 3 cases, you can have as many as different cases. Input option. Okay. Let's go to the plots. So these are the plots. And what I'm interested for these 3 different cases, drawdown, I'm interested to use to see the cumulative, right? Let me deactivate the base case and expand this. Now it is time to do some analysis, right? So you can see for the aggressive case, it's kind of accelerated reserve after 170 days is producing above medium and hard, but towards the end of the production history, definitely underpredicting. How about the medium case? So I'm also interested. I wish I had also included another case here, which was the very slow drawdown, and this drawdown it all the way from day one all the way to 1,000 days, the simulation time, right? And draw down very slowly to see if it's going to be the one that I'm expecting. Yes, let's try it quickly here. So I'm going to add another case here. 3 cases so far generated, case number 4, and I'm going to slow it down very slow. And by very slow, maybe from instead of 445, I'm going to put 1,000. So going to be very gentle drawdown, right? Let's see how it compares against all the rest of them. So this is a slow, save, and run it on the plot. So space case, let's say look at the slow drawdown. So if you are not interested to make money upfront and you can wait for 3 years, this is the one that is producing the most oil EUR for you. Very interesting, right? So you may argue, what could be the reason for that? So the answer to our clients was, yes, there should be some effect of the drawdown. So this is the question. We have evidence. So apparently those evidence are very legit evidence to suggest that pulling on our wells too hard, excessive drawdown result in the lower EUR is very consistent with the physics-based numerical model. So these are very interesting functionality of numerical model that you can rely on, not only sensitivity. So this is simply the phase behavior part of the problem, right? When you pull the valve so hard, the gas also break out of the solution very quickly. And gas breaking out of the solution also reduce relative permeability to oil quite significantly. At the same time, gas getting out of the solution, the viscosity of oil also drop. And what's the governing parameters that tells you how much oil you are producing is basically the mobility of the oil, which is relative permeability to oil to viscosity. So if you're drawing hard, you're also pulling gas out of the solution, which not only reducing the relative permeability to oil, but also increasing its viscosity. So overall effect would be reduced mobility of the oil. That's why you are producing less oil in this case. So it was very nicely demonstrated here that, but at the same time, it's also is the economics of the problem. So you need to include the time into that because time is money. The more you have access to the oil, also it's a critical part here. So it's not all the pictures that we are painting. We need to include other parameters as well, but at least from reservoir engineering standpoints, everything is making sense, consistent to our guts and the oil reservoir. I'm expecting similar exercise to be conducted for the gas condensate because there also condensate drop out of the solution. And the most important commodity that you are making money out of is a condensate on the surface. Because as soon as you drop it out in the reservoir, it is lost. We don't have access to that anymore unless we do some enhanced oil recovery. So you can see the sensitivity. There are a lot of application on the sensitivity, and this is one part of that. The other piece that you can do is people talk much about that is about pressure dependent permeability. So if you pull hard on the valve, they're going to be open crushing, embedment, those sort of stuff. Those phenomena is usually irreversible, right? So we can also do the same exercise, the same drawdown strategy, different drawdown strategy using pressure dependent parameter for fracture. So those are some of the studies that you can do by yourself. And okay, let's proceed. And this is the example for the sensitivity. We can do many other examples for, okay, let's another part of this is probabilistic. So with the probabilistic, we are communicating all the uncertainty that we have in different parameters. I'm going to quickly show you how it works. And the example is going to be a synthetic example, but because through probabilistic practice will be at least 300 runs of simulation data, so we can generate a distribution of the parameter that falls into the solution. So we're finding all the solution in the space that can give you a good history match result that pass that threshold for the error of history match that we saw. And so those are all viable solution, different realization of the fracture and reservoir. And the forecast, however, each of those have generated a different forecast. And those forecasts are important, the distribution of the forecasts that are important for us. And also the distribution of the parameters like XF XF can vary all the way from 200 to 400 that directly impact your well spacing and development plan, right? So you need to know what's your P50 or for XF. What's the P50 for permeability, because that also impact the fracture spacing and also well spacing, two critical parameters that drive the economics of the problem. So that's why we run everything. We should run everything probabilistic. Deterministic is the first pass. We set the stage for probabilistic. And let's quickly run one probabilistic. If you go to wells, you're welcome to follow me, but in the interest of time, maybe I do these a little bit quicker. Probabilistic, quickly name that. And I'm going to leave everything defaulted. And in the numerical model, and run numerical model. This is the first case. So I can now move to the probabilistic. It is just beside sensitivity. And again, very similar in terms of the interface, sensitive to sensitivity. So for the probabilistic, now I can define different parameters, right? What are the range of uncertainty? Is it initial reservoir pressure? So I can select matrix permeability and maybe fracture gamma as well as the rock compressibility. You can select as many of these parameters as you wish, but remember, as soon as you add to your list of the uncertain parameter, you need more runs to do those Monte Carlo simulations as well. So click on next, and there here you start to set some limits. So what is the best distribution type for the matrix permeability? It's probably a log normal distribution, depending that if you have some information on the max, mean, and mean of the distribution. For the fracture gamma, I'm gonna call it a uniform distribution. It may change all the way from 0, and I have some evidence from, for instance, the build-up data that 4 is also on the higher end of the distribution. And for rock compressibility, I'm gonna call it a kind of triangular, and the minimum is to be maybe 2. The maximum maximum could be as high as 15, and peak be maybe 10, right? So this is a triangular distribution. For this one, I guess I have to set it to 2 plus 15, 2 plus 16, and should be 9. Yeah, okay. So this is the distribution. And then so there is also weight factor, right? We don't want to honor the water rate, or the gas rate we know is not very accurate, so we only honor the bottom hole pressure or oil rate or whatever confidence you have in those information, and click on save. And then there's also, you see in the weight factor, said, okay, how many runs do you want to accomplish? So the maximum that's allowed is 1,000, but to be on the safe side and get a meaningful result, anywhere between 100 to 300, depending on the variable space that you are investigating, should be fine. Now we're going to set it to only 10, just for the demonstration purpose. And once you set that up, then you can click on run. And usually, because the grid refinement is set to low, and it is usually we get a very quick answer. So you can imagine if you have some production data, they try to honor the production data and then do the forecast. So at the end of the day, what really matters is the P10, P50, P90 on our cumulative forecast, right? So this is how we set up the probabilistic part of the story. And with that, we already took our break. So we're going to quickly demonstrate the multi-well functionality that we have. And maybe before that, quickly on the enhanced feature that we have. So all the enhanced feature, we have already covered a couple of them, is the different layers that we can accommodate in the software. So we can have different layers with different properties and different permeabilities, etc., etc. If you are believe that that multi-layer better represent the, it's a descriptive of the reservoir. We also have absorption. especially for high TOC content. So it is this information that you can achieve through, it's only absorption is valid for dry gas, not for the oil reservoir. That makes sense for the dry gas to have this. So if you see this option is grayed out for other different type of the fluid system, maybe because those fluid system are not the dry gas. These are some maths you can always actually get to those maths in the manual. And pressure dependent permeability, we have already addressed this. The best information that we can have in order to the workflow, the recommended workflow is to have different drawdown and build-up data. So focusing on both drawdown and build-up data, really, we can adjust those PDP parameters to come up with proper descriptive gamma for fracture and matrix. And this is how we can achieve it. We have already added some of these. And with the PDP, this is basically productivity loss. There are different functionality that you can basically take advantage in order to see, well, the productivity loss only have because we have some testing in the lab that our propans only shows some crushing at the threshold for crushing is 5,000 psi. So we're gonna set 5,000 psi to be the pressure at which the permeability doesn't change with the pressure, right? So these are some functionality that we have. So in the remaining of the time, I would like to present you the multi-well functionality, and it's a lot of application for multi-well, especially when it comes to a study infill drilling, right? You have multi-well that you have been producing for a while, maybe 3 years. Now you're gonna see what's the opportunity of drilling another well in between or somewhere in your pad, and specifically it honors the pressure depletion part, right? Because once we have some wells on production, there are some area of depletions, and we can have those depletion questions get answered into the multi-well. So let's go ahead and go to the well section. At least we need to define one well, so we can call it into multi-well. So I'm gonna add another well here and call it P1, P representing for parent, and I'm gonna call it into multi-well functionality. So P multi-well. I can pick any name that you wish and click on save. And again, we need to define reservoir fluid composition for that well. I would suggest keeping that as is, but you can pick any numbers that you wish. And in terms of the multi-well numerical model, we have that set up in the multi-well analysis section. So if you click on the multi-well numerical model, then they're going to be very similar to interface as the rest of the modules in different part of the software. So we can have many different scenarios for multi-well functionality. So in this case, I'm going to add one multi-well. And again, same interface, same functionality. So the one that I'm interested to call into multi-well is this P multi-well that showed at the bottom of the list. So P multi-well, once selected, then add multi-well model and add multi-well model. And once you click on the multi-well model, you will be in this interface. So this interface very similar to the single well analysis, but with some added feature to accommodate those changes that we wish to see into in the multi-well module. So let's see what we got here. So relative permeability is identical to the single well. Fluid initialization is also identical, but it is required, okay, which PVT of the well from the wells would you like to use as the fluid initialization? So we're gonna call that PVT multi-well and then click on save. So my fluid initialization is set up. On the well and reservoir data, so on the well and reservoir data, this is also very similar to the single well. And now I'm gonna add two more layers. Let's imagine that we have like a wine rack completion and we're going to add different walls and different benches, and therefore we're going to deal with different layers, maybe 4 layers. And each of these layers, we can set different properties. So if they have different thicknesses, different benches, different thicknesses. So maybe start with 50. I can change, adjust it to 60. Maybe the third layer is a little bit thicker, and 4 layers is maybe 20. Right. And the permeability is the most prolific permeability is the second layer. So I'm going to call it 800, and third one again back to 200, and the lower one is also high permeability. That's why we're going to complete that one as well. With the porosity, let's call all the porosity, all the layers have identical porosity. It's very similar to Excel. You can go to the edge of the cell and drag it downward. So the porosity, and at the bottom, it gives you some sort of averaging. So it will be interesting. I haven't done that, but it's going to be a very interesting exercise to generate the same, the one single layer model, but input these total properties as the representative fluid, the representative reservoir properties. Fracture gamma, matrix gamma, and rock compressibility, same as a single well. Click on save. And then in the well and fracture data, it is where we can have different layers. So these are all the 4 different layers that we had. And imagine we have also 4 layers, 4 wells, right? So there are two of the wells are by default included here. And let's see, I'm going to complete this second wellbore, which is here, and I'm going to complete it in the third layer. So to be able to do that, say the perforated layer is a third layer. So you see the wellbore is completed in the third layer, and the fracture layers is also limited to the third layer and fourth layer. So I can find it to the third and fourth. So once I do that, the well will be shifted down, as well as the fracture. And also I can adjust the fracture half-length because these are higher permeability layers. Therefore, maybe I go with a lower XF. Maybe 300 should be fine. And sorry, this is the second well. So second well, 300. Similar to the force wall, let's complete it into the third layer as well. So force wall, this is force wall, and also layer 3, and also 3 and 4. Okay, so this is the one. And then we can also adjust the relative distances between the boundaries and also the adjacent wall, right? So these are maybe distance to boundary is 800. So this will be adjusted itself. Distance to the next wall is 1,000 in this case. Maybe it is 800 as well. The next wall is maybe it is 1,500. So you see how it is adjusting themselves. And then you can click save. And then we already talked about fluid initialization as well as relative permeability section. This is the edit well schedule, right? So if the wells have some production history, you can call which of these boundary conditions would you like to design, would you like to assign to your wells. So because our wells is kind of synthetic, so we're going to select synthetic wells for all of them. And here is the profile for the synthetic. And you can also say, okay, these are the part that you can introduce which well is your parent well, so has been on production maybe for 3 years, and then the infill wells comes into production. So to show you that to you, so maybe call this one to be on production for 1,000 days, and the second well started 300 days after the first well, but we need to accomplish all of this in 1,000 days. Therefore, to be able to finish after 1,000 days, I'm gonna set it to 700 as well, right? And let's keep the rest of them as is. And so this is the edit well section. And again, similar functionality as we discussed in the numerical model is for the grid refinement, time stepping, and also how would you like to run the time stepping. And click on run. Hopefully I did everything in input parameter okay, so it's running because it's 4 wells and also 4 layers. So it's taking a little bit of more time, but we're gonna see how the result will shake out. But in the meantime, let us see what we are left on the we already covered a lot of this stuff, right? We can also have different layers. Also, we can, if we want to have models from flow from beyond tip of fracture, also from beyond top and bottom of the fractures. We also have those functionality by setting H and HF not equal to X and XE. These are the functionality here, so we can toggle them off and adjust accordingly. We also have enhanced fracture regions. So there are some documentation that shows that the fracture may not be easy bilinear. There could be some branch fracture. Those branch fracture, at the end of the day, will cause some permeability around the fracture to be elevated, and those elevated permeability, we can define them as enhanced fracture region with some permeability higher than the matrix permeability. So those are another knobs to turn, but we need to be careful how we may take advantage of that. Simply, it doesn't make sense if we use them if we are getting a good match, because it's helping us to get a good match. Simply we have because we have another degree of freedom, right? But this may not be a representative and descriptive of what's really happening into the reservoir. And we can have fracture extending a different length around the horizontal wellbore. So these are because maybe there is one valves that depleting one side of the wellbore higher, so fractures have higher tendency to propagate in that direction because of the depletion. So we can also have those functionality with the FCD. You can also have a profile of FCD because you know that the completion was in such a way that we started with the 100 mesh, maybe then change it to 30-70, 60-40, those sort of stuff. So there are another functionality, right? Is it recommended? Depends if you're consistent between all of the wells, and without this, if you are not able to do, considering all the uncertainty that we have with the bottom hole pressure and rate, etc. We have also some fracture at an angle, so those are also capable to include them simply because you are not drilling the well in the direction of minimum or maximum horizontal stress. Therefore, some of these fractures turn to align themselves based on the stress regime. So we have those capabilities as well. So apparently I have higher layers, but I can quickly show you the result from them as well. So at the end of the day, running those numerical simulation can be really helpful to showcase if the FCD is lower, how would the buildup look like, right? And if there are also some field observation. So I purposely included this slide as the field as an indication of how you can tell the same story using different part of the data and how we can demonstrate using numerical simulation tools as well. And integrated part of all of these is the analytical space, right? Because analytical space talk about a slope. We don't see that in the numerical simulation. Analytical space talk about intercept, and we don't see that in numerical simulation. So we're gonna start from analytical domain and use those information as our guidelines to adjust the parameters into numerical space. So these are again some information, and I guess we already covered the basics. And 1 minute left. Hopefully you enjoyed the course. I can see 57 people stay online, which is huge, and great news for me. It's the first time Whitson offered this course. Hopefully everybody will enjoy. If you have any question, please don't hesitate. I would be willing to have a separate session with each of you as much as needed to go through these and basically have an in-depth discussion on that. Hopefully, I will have the pleasure to see some of you in person next week during VidCon, and looking forward to shaking hands and greeting you guys there. Enjoy the rest of the day, and let's stay in touch.